So hello everyone. I'm going to talk about the use of phase field method for heterogeneous material. First, I would like to acknowledge some professors and PhD students that helped me for this work. The main motivation of this work is to increase the accuracy of non-functional prediction using finite element analysis based on the CT scan data. To achieve that, we would like to investigate the phase field method for ball, which is a heterogeneous material. The main advantages to use this phase field method is that we don't need to remesh to track crack initiation and propagation. We can represent complex fracture path and crack bifurcation, and also we can account for compressive strengths that in case of bond can induce fracture. And for example, this is an example of a problem of an experiment on humeral bond under compression that we would like to tackle with this method. And the main challenges related to such a problem are the heterogeneity of the bond, because the phase field method has been originally developed for homogeneous material, and so we need to have a good phase field theory derived for heterogeneous material, and also a robust finite element implementation to solve this kind of problem. So for that reason, I will start to present some analytical solutions for a 1D heterogeneous bar using the 81 phase field model. The general framework has been proposed in this work of Francesco Vincentini, and basically we have a 1D bar of length L and a prescribed stress sigma T. We use the 81 model, and there are three cases that are considered of heterogeneity that are considered in this work. In all the cases, we have a minimum value for the E of X, the Young modulus, and the GC of X, the fracture toughness. This minimum value is at the center of the bar, and we have three types of variations. We have a linear profile, parabolic and exponential variations, so three cases. And also in this analytical framework, the irreversibility is not considered, and we would like to derive explicit analytical solutions for this problem, and in order to verify the finite element results from any phase field code using finite element. So, for example, for the linear profile, so we can see three phases. There is an elastic phase where you don't have damage until elastic stress, sigma E. Beyond this stress, there is a phase of damage, but before failure, it means that the damage variable is higher than 0, but lower than 1. And there is, beyond big stress, which is the maximum stress, there is a failure phase where alpha is equal to 1, which corresponds to the fracture of the matter. The interesting thing here is that for a classic homogeneous case, the phase field, the size of the damage band is related to the L0, which is the internal length of the phase field model. Generally, for each side is 2 times L0, but for the heterogeneous case, we observe that this damage size band is smaller than 2 times L0 for each side. So it's quite different from the classic homogeneous case. So we also have the results for the free physics for exponential profile. For parabolic profile, the analytical solution for the failure phase is not completely available in this work. And from that, we can infer the stress displacement curves of the three profiles, the linear and exponential and the parabolic profile. The main interesting things are that, as it has been really already said, for the homogeneous case, which is in dot line, we observe a lower peak stress than for the heterogeneous case because we have lower E and GC values around the middle of the bar. And also we have the interesting thing is that we have a snapback phase after the peak stress in the two cases, homogeneous and heterogeneous cases. And to obtain these values for the snapback, we need to solve this, the damage criteria starting from sigma T equals 0, and then we can deduce the values corresponding to the snapback. So now the interesting thing is to compare these analytical results with finite element results. For this 1D heterogeneous bar, we use the MATLAB code and a potential energy minimization with respect to the displacement U and the damage variable alpha. a staggered solver scheme is adopted to solve this problem, and for the finite element analysis, it is a displacement that is prescribed, not stress. And as I said at the beginning, the analytical framework does not consider any irreversibility, so we wanted to don't consider any irreversibility condition also in the finite element implementation. However, we observe, for example, for the elastic phase, that if we start in the damage solver, if we start by a value 0 for damage, which is actually the solution for this phase, the elastic phase, we end up to a solution of alpha with negative values at the end of the solving process. It means that there are several local minimizers to this problem, and some of them have negative values of alpha, and these are not admissible solutions for phase field, and so that's why we need to impose the recovery constraint, which is a positivity constraint. It means that alpha needs to be higher or equal than 0, which is different from the irreversibility constraint that says that alpha, the derivative of alpha is higher or equal than 0. To enforce this positivity constraint, we use the penalization technique that has been proposed in this paper of Gerasimov and Lorenzi. It consists to add in the variational formulation of the potential energy a penalty term, green, and that depends on the penalty constant ρ, that has to be n of big to penalize the energy if the positivity is not respected, but without causing ill conditioning issues. In this paper, they propose an optimal value for this penalty constant for a 1D homogeneous bar in A21 model. And in our case, we assume that the GC value is the maximum of GC of X, because we are considering an heterogeneous bar. We also need the recovery tolerance to keep the gamma covariance property, and the main advantages of this technique is that we can keep the variational framework of the phase field, and there is no explicit constraint imposed on the damage variable alpha. So we want to estimate the error for a linear profile E of X and GC of X. But we need to remember that, as it has been said in this paper on Bourdin, when we implement H version of finite element analysis of the phase field, there is an overestimating of the GC value in the numerics. So that's why in this paper they propose a correction factor to correct this overestimation. And this factor depends on the mesh size and H and on the L0, which is the internal length of the phase fields. So if we want to do a convergence analysis by taking two different meshes, we don't consider this correction factor. We are comparing two different problems because we have two different GC in our two problems. So that's why it's important to consider this correction factor. And in our case, which is an heterogeneous bar, we assume that the correction factor is similar to the one that has been proposed for the homogeneous one bar and the homogeneous material. And so we are using two different mesh size, H, and also two different penalty constants. One which is the optimal one, which is 1000, it's in blue, and an higher one, which is 10 to the power 9, which is in red. So we observe that for the elastic phase, means no damage, we have less error when we use the high value of penalty constant. But if we zoom on, for example, this results for the high penalty constant, you observe that the final mesh, which is the straight line, does not give better results than the coarser mesh, which is the dotted line. And so this can be related to the influence of the GC correction, because the elastic stress, the limit elastic stress, depends on this GC of X, and so we need to investigate that. However, for the phase of damage before failure, we observe that the error decreases with refinement and with penalization. For the failure phase, for the displacement, we observe high error in displacement at the crack zone and no influence of the penalty constant. But for the damage, we still observe that the error decreases with refinement, but the optimal penalty, which is the lowest one, gives better result on the damage localization band, which is here. So this is an example of a comparison between numerical results and analytical ones, but we can also compare numerical results with experimental observations. And so that's why I want to talk about this preliminary phase field code for humeral bone. So if you remember well, I presented this problem at the beginning, which is the compression of a numeral bone. So we are using a linear mesh, but that has been built from CT scan. And for the heterogeneous material property, we are using a heterogeneous Young modulus E of X that has been extracted from CT scan data. And for the fracture toughness, we are using an assumed correlation with the Young modulus E of X. And this correlation, which is this one, is calibrated with these parameters with experimental results in this paper. We are using a Phoenix code for the phase field model, and in that case, we are imposing the reversibility constraint. We observe that if we only consider the heterogeneous Young modulus E of X, we have a complete different fracture location in the simulation than in the experiment, where you see that the fracture location is around the neck. But when we consider both the heterogeneous Young modulus and the heterogeneous fracture toughness GC of X, thanks to this assumed correlation and calibrated correlation, we obtain better results in terms of fracture location comparing to the experimental one. So for the further work, we want to do this simulation with quadratic elements to be better accurate, and also we want to verify these numerical results thanks to the benchmark, this analytical solution that you obtain for the 1D problem, to do this numerical validation with the analytical results. So as a conclusion, we explicitly derive analytical solutions for the 81 model and heterogeneous 1D bar that can be used to verify the results of finite element codes. We also perform an H finite element analysis, the H version of finite element analysis with penalization, and we still need to investigate how we should use this penalization technique for heterogeneous materials with varying E of X and GC of X. We also observe that there is a difference in the penalization results for the phase when it is completely fractured and the two other phases, the elastic one and the partially damaged phase. So that's why we need also to investigate the calibration of this penalty constant for an heterogeneous GC of X. We also observe that the numerical errors decrease with final mesh, except for this case, when we are at the elastic stress. So we also need to investigate the GC correction factor for heterogeneous GC of X, and also for P version of finite element analysis, because it's also used for bone simulation. And also you remark that in the profile of heterogeneity that we presented, the minimum value of E of X and GC of X were at the same location, but it will be interesting to study where these two minimums are not coincident. And also we would like to extend this analytical framework to heterogeneous 3D domains. Finally, the bone fracture location validation using this preliminary Phoenix code for phase field and the calibrated GC of X expression highlights the importance to account for both heterogeneity in both Young modulus and fracture toughness to use phase field for bone fracture prediction. Thank you for your attention.
Thank you, Maxime, for that very nice presentation, which is open for discussion.
I have a question regarding this non-recovery constraint you said.
Yes.
So it basically says that the damage variable cannot go negative. However, it must not increase, so it can go down again.
This is when because when we are dealing with like snapshot of you are prescribing stress, sigma t,
yeah,
or a displacement, and you are not dealing with loading history. So there is no
you basically solve
exactly. We are dealing with snapshot. Comparing the solution at this snapshot to have an analytical solution for prescribed load, like a classic benchmark. I give you a load, displacement stress, and I want to see if I obtain all accurate RMI results for these prescribed conditions.
Okay.
So that's why the read just
because you basically don't care about the history.
Exactly, because it's the benchmark for a prescribed loading condition.
Thanks.
Well,
Are there more questions? Maybe I have one or two regarding the experimental characterization. I mean, now you assume the GEC to be proportional to the Young's modulus. I mean, are you also planning experiments to get these values individually? I mean, you do that.
yes, that's my second. My second job in the PhD is to find experimental assessment of the dependency of the GC on the Young modulus or on the bone density in the bone. And so that's I plan to do experiments. It's in preparation to obtain experimental data on this, but with this assumed correlation, with the calibration of the parameters, even accurate results have been obtained, but there is no experimental assessment or base to this correlation. So that's my second job that I need to join my PhD.
I have a question. You related CT with the density with the elasticity, right?
The CT scan?
Yes, you related CT with the density, density with the elasticity. And you are relating now elasticity with the factor numbers. So every element will have different factor numbers, right?
Yes. The factor toughness is heterogeneous, so we think that at different locations on the bone there are different values of factor toughness, like there are for Young modulus values.
Yeah, maybe we should shift the last question to the coffee break, maybe, because I have to keep an eye on the time. So thanks again.